Steady state thermal loading can be set up in Aspire using the temperatures setup tool. Allows you to apply a temperature difference to a part or multiple parts in your model. So look at this typical heatsink type example. So there's a heatsink fastened to two brackets. So we can apply a thermal loading. In this case we'll type in 100. That's a 100 degrees temperature difference. So that will cause the heatsink to expand. So we won't apply loading to the brackets, but we do need to constrain them. So we'll just attach them, ground them out. So we've got a temperature difference on the model. The parts are attached or grounded. So we'll run it and have a look at the results. The run's completed. Let's load the results. We can see the model is loaded. There are stresses, and have a quick look at the animation. So you can see the heatsink is expanding and bending the brackets as you'd expect. We'll look at the displacements. You can see 0.4 millimeters. So that's a realistic kind of displacement. Now the way that this is calculated, if we look at the materials in Inspire, we have a thermal expansion coefficient on the materials. So you can change that thermal expansion coefficient depending on your material property, which will of course affect how much it expands when thermally loaded, and hence how your structure responds. The accelerations tool allows G-loading and angular velocity and acceleration to be applied to an entire model. For the G-loading, just pick the tool, pick any component, enter the G-loading you want to apply. You can orient with the principal axes, and you can also reorient by rotating using the tool. The acceleration is applied in a similar way. Choose the tool, pick any component. Now here you can also reorient and ensure that the acceleration axis is in the correct location. So we've just reoriented it onto the center of the flywheel here. You can also change the angle of orientation. We'll leave it in the center. You define the rotational speed in RPM. We assume this is a flywheel on a typical automotive engine. About 6,000 RPM is a reasonable number. You can also have an angular acceleration in radians per second squared. If you imagine this is bolted to a crankshaft, we could apply the supports. Control Z to go back when I applied the support in the wrong location. So we've applied those. Now analyze this. We'll just make it fast and run. With the results completed, we can load them in, and if we animate, we'll see an expected deflection. Introducing section cut tool, we can choose any point on the model to apply a section to, a cut to. We can now see the animation on that section. We could reorient it by choosing different axes or even rotate the section. Enforced displacements can be applied using the displacements tool. So you can see this plastic clip, imagine it's sliding into a buckle type housing. So as it slides in, it has to displace a set amount. So we can measure quickly roughly what that displacement that's going to need to be at that point there is. So it's 2 millimeter. So what we can do is use the apply enforced displacements, that edge there. We want it in the Y direction, and we actually want it in the opposite direction. And And what you can see when that displacement's created is the actual true distance that it will move. You can see that is that 2mm depth that we're after. I want to apply it to the other edge as well on the opposite side. Spin the model around. Again, switch direction, and the enforced displacements are in the right direction. Now we can constrain our model just on the back edge here, back face, and run an analysis. So this will apply those enforced displacements and give us the results. You can see we can now load the results in, and we've got the stress state in the model. So if we look at displacements, we expect that where the loads were applied or the displacements were applied to be around 2mm, and if we just grab the threshold in there, we can see that that is very close to the 2mm that we expect.